Hello, Dr. Raff. This is Miles Franklin for the Data 690 final this semester. The project that I tried to accomplish was taking black and white photos and training a model to learn color for those photos in a smart way. I tried a collection of models, as we can see in bold, a GAN, WGAN, convolutional neural network, fully connected autoencoder, and a convolutional autoencoder. Um, and a lot of the reason for so many models was just never got the results that I was looking for. Looking at the last of these, the convolutional autoencoder is the best model that we had, or that I ended up coming up with, but still kind of important to note, like still didn't really do the job that I was hoping for. Does a good job of returning the original image, but not such a great job actually adding the color as hoped for. So skipping over imports, looking at the data that I used, I took labeled faces in the wild from Torch Vision, and labeled faces in the wild is kind of as described. It's just a collection of faces. I think size 250 by 250. It's a pretty good size data set that I decided to work with. Coming back up here, there are some other data sets that I was like curious of running on just to see if I had a working model, what the best use case would be if it was easier to learn, let's say like landscape color schemes as opposed to human faces for color scheme. So that was just like an idea that I had when I was originally going through the model, but again, never got to the desired results to really look to see how it handles different data sets. But that's the one that we went with for, at least that I went with for this project, LFW. And so the first approach that I went was that I started in RAM, and don't think I really realized that going into it, but needless to say, like really quickly ran out of RAM, and I had to store the data on disk and then read each file as needed. So yeah, as we can see, made a dataset class for LFW, called it LFW old, and was saving everything in just massive arrays. So that wasn't the right approach, hence no longer in use. And so I have this version of LFW that actually works. So first bit of code just makes train and test folder, just because for whatever reason they won't dynamically make it on their own. Some of the other libraries. And if we just kind of start with the constructor, we see paths. That's the list of paths to all the images that are downloaded from Torch Vision. Training, so that lets me know if I'm in the testing folder or the training folder, and then lab. And so we'll come back to this one a little bit, but basically I spent like a great deal of time in this project trying to figure out what's the best way to represent the data in lab space or in RGB space. So basically, this goes through all of the paths from that pass object, or that pass parameter that we sent through. Takes the image, gives me they start with a color image. I take that color image, I resize it to 256. That was just so that I could have an easier time with switching through dimensions later on in some of the models. And then once I have my color image, I create a black and white version of it, and then I save the black and white image. So now just kind of dive a little bit deeper into what's going on with like the lab variable. I actually have a slide deck, so we'll take a look at that. Boom, boom, boom. So the difference between RGB space and lab space is RGB has 3 channels that correspond with how much red, how much green, how much blue, and then lab has 3 channels again, but instead it has how much black and white, or how much brightness, a spectrum from green to red, and then a spectrum from blue to yellow. So those are so that's the main high level difference between RGB and lab. At first I was using RGB just because I thought that was the most logical way, and I hadn't heard of LabSpace prior to. And then after looking at a lot of other projects, just a lot of other like resources online, I started to notice that LabSpace was the more common approach to this project. So start with RGB and ended up going with Lab, and then this next slide does I think the best job of explaining like why LabSpace is the best for this particular problem. Basically, in a black and white or a grayscale image, the A and the B channel are just completely zeroed out. We just have values of black and white, which are just all in the L channel. So the way to, I guess, logically think of this problem is that we're going, given a channel L, can we predict the other two channels A and B? And so once I made that connection, I was like, oh, okay, this might be the right way to represent this problem. Unfortunately, the problem that I ran into, we can exit out of this and come on over here again. Fortunately, the problem that I ran into with this approach was that when lab is false, so we're not representing images in LabSpace, we're doing them in RGB space. Really easy to size images because images can get normalized down to 0 and 1. But for LabSpace, let's see. Yeah, we can see it still wasn't really sure how to even approach the code, or at least like bring it from Scrapwork into here. LabSpace for the A and B channels, or I guess starting with the L channel. The L channel goes from 0 to 100, so it's really easy to scale down to 0 to 100 to normalize it. But for the A and B channels, it goes from negative A to negative B, negative A to positive A and negative B to positive B. So that presents two problems. The first one is that it's really difficult to scale it down just because A and B were really arbitrary values, and I couldn't find what the maximum value was anywhere. So that was really kind of bizarre, to be honest, like looking through the documentation on it. And then number two, it made it really difficult to figure out what's the appropriate activation function. So the way that I approached it, which we'll see in a little bit, is that I decided to use sigmoid function for RGB space because that maps to 0 to 1, and that's where all my values are. And then I tried hyperbolic tangent function for when I was in LabSpace. But again, we have the problem of scaling, so it would presumably, or even if not even presumably, if we were to assume that it was actually printing out like the right values or the right distribution of values, there was no real way to, at least like that wasn't obvious to me at the time, there was no way to learn by what value should I scale those values from that AB, or from that like 0, like negative 1 to 1 range. Like I didn't know what the maximum range was, so I had no idea like what function could map the prediction to the actual value. So that was where I spent a great deal of my time on the project, and that's more or less where we are with that. And then from there, pretty straightforward. Cast everything as a tensor, and then save that tensor to a value. So each value is, if you were to index it, let's say i.pt, when you go to the dataset object or the LFW object, you could say LFW bracket I, and it'll just come grab it from this file. And we see that here in the get item. It's exactly what it does. It just loads that value from inputs at that ID, and then just returns the black and white and the colored version of the image. So here, nothing crazy, batch size of 1 just for simplicity's sake. Lab is equal to true in this case, and then just reading all the data in from Torch Vision, casting it in that data set object that I wanted, and then putting that in a data loader so that it's easy to hand off to the training object, or to the training object. Let's see. Here's just a bit of a sanity check. So wanted to make sure that targets and inputs were bounded with what I wanted it to be in. So I think the last time I ran this, then lab must have been false, because training or the black and white and the color image of this are both bounded within 0 to 1. So probably an RGB space with this one. Here, just some good helper functions. Plot black and white image, takes that lab parameter as well, and then plot the color image, and basically just kind of does as we expect. Takes the image as an object, scales it if needed, and returns it. So I used to have plt.show, but just for playing around sakes, just you can plt.show afterwards if you end up playing around with this. So this is our first image in the data set. Too young to know who this is, but that's a black and white version of them and a color version of them. Not going to go too far into depth of this, but just open it just to show you, just so you have an idea of what's going on. This is me, as far as scrap work, just trying to figure out what's the best way to scale and represent LAB space. So this is like a lot of the logic that I was probably going to throw back, up here in this like normalize and min-max scale. Like I said, I couldn't figure out the cleanest way to do it, so I decided to just leave it in a scrap cell and just keep this dataset class clean. But let's come back down, and that's already closed. All right, so for the modeling section, just kind of establishing some variables, see what would be helpful. Height and width, latent dimension. I kind of toggled back and forth between using the latent dimension just because I wasn't sure if I wanted to learn like a 1D latent dimension or if I wanted to just learn like an image instead of a dimension, or like a 1D dimension. So that was just something that I was trying to figure out. Neurons outshape epochs. I guess nothing crazy here to report. This reference scan is just a GAN that we took just straight from the book, just so I had something to model it after. And like I said, I think I follow, for the most part, a fairly similar process. I think mine is, I actually never ended up using this add noise, but just because I never got good results without it. But basically, I was just trying to figure out a way to add some noise to each image to add some like robustness to the model. But like I said, never got around to that. So yeah, let's close this setup because I think that's just more or less stuff from you that I use as reference. And then I don't need to open up Scrapwork here. So yeah, here's my GAN. So we can see some of the things that are commented out, because I just try to strip it down to the most basic level before I did anything else. I think at a certain point I was just trying to make sure that like G worked. But for sanity's sake or cleanliness sake, we can just uncomment that. So I was trying to basically run a series of convolutions on the model, not changing the size of the model, so same dimensions or channels, stride of 1, padding of 1, so just a pretty basic pattern of convolution, ReLU, and then an output of sigmoid, because like I said, for RGB space, I wanted to have my values bounded between 0 and 1. And then some of this down here, which is also commented out, was when I wanted to, I think I've deleted some stuff like since then. But at the time, I tried to flatten this down to a linear layer, tried to learn like that latent dimension, and then hand it back out to the discriminator.